Alright, so where are we in the course? If you think about what we have done so far, we started by saying that look, solving a new problem is the cornerstone of AI. Problem solving is the central theme of any intelligence. And so we decided on one general problem representation and we talked about how to solve that particular problem. So, general problem representation was the atomic agent and how we solved it was using a lot of search techniques. And then we said that that is awesome, but we need to build in knowledge in the agent. The agent can't be starting from scratch every time. If I want to basically use minimax till the very end, I will never make a good chess player. I have to give it some knowledge, some kind of knowledge. So, we asked the question, how would we give that kind of knowledge? And to give that kind of knowledge, we learnt two main knowledge representation languages. One was the language of logic and one is the language of Bayesian networks. A Bayesian network gives us how the various variables in the state interact with each other. A logical representation also gives us how do the various variables in the state interact with each other. Logical representation gives you logical way of doing this, implications and rules that may be true deterministically in my system, and Bayesian networks give the same in a probabilistic way of thinking, in the probabilistic relationships, right. I thought this is a good time to take a step back and think about what we have accomplished, how does it fit together and how does it fit with the initial philosophical definition of AI that we started with. Now, typically people teach this set of slides right after the introduction, but I feel that the introduction is already too long and these set of slides are really well understood when we have done some parts of AI and we are going to do some others, so that we can sort of see how they fit together. Okay. So, this is what I am going to do today. I am going to talk again about agents and environments and rationality, which is what we had come up with as the definition of AI. And then we will talk about the various kinds of environment types and we will try to see what we have studied, how it fits together in different environment types and different agent types. Okay. So, this is our goal. It is not going to be a very technical lecture today, but it is a lecture where it is important to take a step back and think about in a big picture where are we, and then we will come back to again something specific that we will study starting the next class. Now, if you go back how we defined an agent, we said that an agent is anything that can be viewed as perceiving the environment through sensors and acting upon the environment through actuators. Okay. So, if you go back to the definition of artificial intelligence, we had even defined AI like this. We said acting rationally, right. If you remember, we said acting rationally, and our definition of acting rationally was to say that okay, I will have a rational agent, it will be observing the world. So, it will be observing the world through an observation sequence or a percept sequence, and then it will have some opportunities, it will take some actions, right. And this action would be one that maximizes its performance measure, optimizes its performance measure on the basis of evidence perceived so far and on the basis of built in knowledge. So, if you think about this in this definition of AI, the idea that AI is an agent in an environment, observing the environment and acting in the environment is central, right. And this observing the environment will happen through its sensors, right, through the percepts, and it will be observed through its sensors, and the actions will be taken through its actuators. So, if you think about humans, we are agents too in this world. What are our sensors? Sense organs, right, eyes, ears, skin, right, tongue, smell, nose, and what are our actuators? How can we change the environment? Through our limbs, right, I can hold this mic, through our voice I can say something in the world, and so on. So, this is we as an agent. Of course, we can have a robotic agent. A robotic agent may have a different set of sensors, a different kind of actuators, right. It may have various motors for actuators, it may have camera and laser range finder as sensors, right. So, we can think about an organism or an agent as the central entity that the AI system is the brain for, right. So, what are many kinds of agents like an AI system is typically controlling? So, a physical agent like so an intelligent building, a building which automatically turns its AC off when it senses that there is nobody in the room, a building that automatically opens the door when it senses that somebody wants to cross the door, a building that automatically reminds you that, oh, you have left your wallet, but you are going into the car, so you should need your driver's license, a building which has all kinds of instruments and gadgets built in which can talk to each other and actually can exercise intelligence. Such kind of intelligent homes are getting built, not necessarily in India, but definitely in the West, right. You must have heard about Nest. Do some of you know about Nest? Nest is this automatic temperature control device which maintains the temperature of your home, and it sort of senses what to do, right. So, it has something built in, but then you increase its temperature, it gets a little bit of data, you decrease its temperature, it gets a little bit of data. It starts to learn that you will leave from office at 11 o'clock, you come back home at 7 o'clock, you know, on the weekends you have this kind of behavior, etc., 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 and it automatically maintains those temperature schedules. You do not have to feed it in, right. It is an intelligent temperature control system. Autonomous spacecraft or even aircraft, the aircrafts all have this autopilot mode. Now, we have intelligent driving cars, they also have an auto drive mode, right. You have spacecrafts which are deciding what to do in the sense of when something is failing, how to deal with it, and so on, right. In fact, at NASA some of my old collaborators had done something very awesome, where they said that if suddenly there is a problem in the aircraft, like this is not working, that is not working, and so on and so forth. Let us say a limb is not working, one of its rotors is not working, it can't maneuver in a standard way. How do you get it to land? Emergency landings. And how can you create automatic algorithms which can get the aircraft to land, right. And there they figured out that, okay, based on the turbulence, based on, you know, it may not be able to go in straight line, it may always be going into the curved line, based on the specific fault that has happened in the aircraft, how do you get the aircraft to land, right. Pretty amazing stuff, right. But not all agents need to be physically grounded, some of them can be digital and soft too, like just this general idea of expert systems. You go to the machine, say I have this symptom, this symptom, this symptom, and the machine figures out what disease you may have and what is your course of treatment. Here there is not an agent which is sort of acting in the world, physical world, it is an agent which is just getting the data as you maybe speak in terms of a signal, or as you type maybe in terms of text, and that is its sensors. And its actuator is what course of treatment it gives you, right. Google is one such example. Its sensors are the keywords that we type, and its effectors are the 10 blue links that it provides, right. IBM Watson is another example of this, where a new question comes in and it has to give an answer, right. So, the bots or the agents need not be physical, they can also be virtual. An intelligent agent not only has sensors and actions, it also has a performance measure, right. It should strive to do the right thing, and a performance measure is the objective criterion for the success of the agent's behavior. And that led us to the definition of AI, where the agent wants to maximize or optimize its performance measure. But it can only optimize it based on what it has seen so far, it does not need to know what it does not know, right. We can't predict the future. An agent, an AI system is not an astrologer. It may have a probability distribution about what happens in the future, but it does not need to explicitly know what is going to happen, how the cards are going to be played out, right. It does not need to know this. It needs to use some built in knowledge, and this built in knowledge will be represented in our knowledge representation language, right. So, this was the point, it has to be rational, but it does not have to be omniscient, right. If it does not know something, it makes the best decision based on what it knows so far, it gets to know something new, that does not make the decision wrong. It may even act in order to obtain valuable information, right. It may make an action which does not change its performance measure, but it gives it some information about the world, which then leads to its performance measure increasing long term, right. Now, this is the ideal rational agent. This rational agent we cannot construct as an AI system, because the problems are NP hard. They are problems which cannot have a polynomial solution today. There are problems which will, if we want to have an ideal optimization of the performance measure, it will just go on and never finish, or the memory will be full or something like that. This is the idealism. This is the definition of intelligence. It is the pinnacle, it is the optimization of the performance metric in a given setting. But in practice, the agent will be what is called bounded rational. It will have bounded rationality. It will be optimizing the performance measure given its knowledge and choosing the best action so far, but given limited computational resources. It will have let us say 1 minute of time to play the game. It will have 2 minutes of time to come up with the solution. It will have 4 GB memory or 8 GB memory. It will be given some limited computational resources, right. So, this is sort of where how AI systems think about themselves. Now, given limited computational resources, we are never reaching the optimal in general, right. So, a more intelligent system would be one which gets to a better performance compared to the other one, right. And that is why we will have rankings of AI systems. It is no different from the chess rankings. Every chess master, grandmaster, regular player, they have some ranking, they have some score, and that score tells us how well they are playing the game. This is also true in tennis, they have ATP rankings and so on and so forth. This is the current state of how well the tennis player is playing. In the same way, in a given situation, an AI system will produce some performance measure, and based on how good the performance measure is, you can rank, and you can say the system which produces better performance is more intelligent. Now, given a new setting, given a new organism, given a new agent, it is worth thinking about for an AI system what is the performance measure, what is the environment, what are the actuators and what are the sensors. This helps us in an intelligent agent design, right. So, let us think about, for example, an automated taxi driver. What is its environment? For an automated taxi driver, what is the environment? The roads, the pedestrians, the trees, right. What are its sensors? The camera, maybe the infrared or the laser range finders. What else? What else sensors might a car have? GPS, very good. A sound recorder for talking to the customers? No. Just to get a sense of how much traffic there is, maybe noise can be an indicator for that. Okay, interesting, right? And so on. What are its actuators? The brake, the gear, the signal, the horn, whatever, right? Those are its actuators. Now, what is its performance measure? How human-like it drives. Kashika says that's a performance measure that I want, but it needs to go somewhere also. Number of accidents, it wants to optimize for those. Hopefully not maximize for those, yes. The total time taken in the trip. How much it follows the traffic rules, right, and so on, right. So, exactly, precisely. So, you can actually list all these things and it's easy to think about the environment, actuators and sensors, but for the performance measure you have to be a little more careful, and you realize that there are many things which are competing. And when there are many performance measures, you have to think about how do I combine all of them to define my optimization problem. And there are many ways to do this. One is to say that I will be legal, I will be safe, and those are constraints, but I will maximize my profit or minimize the time, and that will be the optimization function. That will be constrained optimization. Another way of saying this is that I have some penalty for being illegal, I have some profit and some dollar value for being profit and so on and so forth, and I will add all of these and define one final objective function, and that would be converting multi objectives into a single combined objective, right. That would be another way of doing this. A third way of doing this is saying, look, I can't compare, so I will just try to come up with all solutions that have that are non dominated, and that is a third way of doing it, which is called multi objective optimization. We are not talking too much about it. So, if you do not understand what is non dominated, you will have to go and read it, but it comes up with a Pareto optimal set of solutions, right. So, those are three different ways: have only a single optimization, everything else is a constraint; create a single optimization which is a combination of all objectives; and third, keep all objectives separate and try to come up with a set of solutions which are all good and can't be said as better than the other. Similarly, you can have a medical diagnosis system, right. In this medical diagnosis system, your environment is the patient, the hospital, the staff, your actuators are the display in which it will give you the treatment or diagnosis or tests. The sensors would be again the same keyboard and so on, where you will enter the symptoms and so on. And its performance measure is, for example, having a healthy patient, but also minimizing costs and minimizing lawsuits, which is extremely important in a health setting, right. Now, let us zoom a little bit in the environment. What are the various properties of the environment? These properties are incredibly important because they help us in figuring out what kind of algorithm to use. One property is observability. Let us spend a few minutes here. Is my problem, is my space fully observable, that I know at every point in time completely about everything in the world, or is it just not observable at all, which is another extreme, which is rarely the case, or is it partially observable, that I can know some things about the world, but I cannot know some things about I do not know some things about the world, right. So, I know who all students are present today, but I do not know where those students are who are absent. So, that is partial observability of the world for my class. Right. Can you give an example of a world which is fully observable? Chess. Chess is fully observable. I know the exact board position at every step of the way. Can you equivalently think of a game which is partially observable? Poker. Very good. Poker is partially observable because I do not know their cards, I only know my cards. Good. Then the environment is deterministic or stochastic. Now, this is self explanatory. When I take an action, I know exactly what is going to happen, that is a deterministic world. When I take an action, different things can happen with different probabilities, that is a stochastic world. An example of a stochastic world is the robot trying to pick up this phone. It moves its it senses, it figures out what kind of shape the phone is, it gets its limbs together, gets its hand, fingers in and tries to pick it up. With a high probability, maybe it picks it up if it is a good robot, but with some probability it misses, or maybe it picks up and the phone falls down. That would be a stochastic world. Then there are episodic versus sequential tasks. An episodic task is a one step task. I give you an image and I say, is there a dog in the image? That is a one step task. You are not playing a sequential long term decision game. Like I give you a CSP and you solve it. That is a one step task. This is the solution. On the other hand, these are sequential tasks. Sequential tasks is I take one action, then I look at what happens, then I take the next action, and I keep playing this sequence of actions. So, if I have to output a sequence of actions, or if I have to play a sequence of actions in the environment, that will be a sequential task. If it is a one step thing, I am just doing face matching and figuring out is there a face in there or is there a terrorist in there, that is a one step task. Then there are things where the environment depends on time or it does not. A static environment versus a dynamic environment. A dynamic environment is when things happen by itself without the agent doing anything. Over time the environment changes by itself, it is a dynamic environment. Like I do not do anything, I keep standing somewhere and suddenly there is rain. This is an environment changing by itself. Most physical environments where the robot has to move around like an automated taxi driver, it is a dynamic environment. If the taxi does not do anything, the world still changes around it. Other cars do move, the cars do go, the lights go red and green, right. It is a dynamic environment. A static environment is when until the agent makes a change, nothing changes. 15 puzzle. 15 puzzle is a static environment. The puzzle pieces do not move until the agent tries to move it. A semi-dynamic environment is an environment where the environment is static, but the agent's performance measure depends on time. Like chess. In chess, have you seen that the player plays a move and hits the clock, stops, hits time, right? Any kind of game gives you a total amount of time, and your performance measure can change if you run out of time, even though the environment has not changed. That is called a semi-dynamic environment. In such environments, it is important to do meta reasoning. It is important to think about how much to think and say that, oh, if I think more, I could possibly get a better move, but my time is running out, let me not think more and stop thinking and make a move and stop my time, right. That would be a behavior in a semi-dynamic environment. Of course, the environment is discrete or continuous, right, whether it has continuous variables or it only has discrete variables. And if it has both, they are also called mixed discrete continuous or hybrid environments. And last but not the least, is there only one agent or are there many agents? And if there are many agents, are they acting together for the same objective? Are they acting against each other, or are they just self-interested? They can be cooperative or competitive depending upon the situation. What are humans? They are self-interested. If you hear the word that humans are always selfish, that means exactly the same thing. They have their own optimization function, and that is what they are optimizing. And of course, they are doing a long term optimization. So, sometimes you would do something for your spouse even though you do not want to do it for the long term happiness of the marriage, right. You do not have that experience, you will soon have it in a few years, I am pretty sure, many of you at least. Whereas in chess, it is a competitive agents, and in if you have a set of robots who are trying to manage disaster, then they will be collaborative, they will be cooperative, right. Let us quickly think about this. So, chess versus robot, right. Is chess a static environment or a semi? It is a semi-dynamic environment. Is it a deterministic or a stochastic environment? Deterministic. Is it observable or partially observable? Fully observable. Is it discrete or continuous? Discrete. Is it sequential or episodic? Sequential. Is it single agent or multi agent? Multi agent, two agents acting against each other, right. So, that is your chess environment. Now, think about a robot which is trying to play soccer. Is it a static environment or a dynamic environment? Dynamic environment, the ball is moving, Is it a deterministic environment or a stochastic environment? Stochastic. You try to hit the ball has gone somewhere else. You saw those videos where the goalie was trying to do interesting things. Is it an observable environment or a partially observable environment? Partially observable. Why? The ball could be behind you, you may not have sensors. Even though you have sensors, you may not exactly know everything because you have uncertainty in the sensors. Is it a discrete environment or a continuous environment? It is in the physical environment, so it is continuous. Is it a sequential game or a episodic game? Sequential, right? You take a sequence of steps, you want to get to a goal. Is it a multi-agent or a single agent? Multi-agent. So, now you can start to see how different environments make the problem more easy or hard. Chess is not an easy problem, but it is much easier than robo soccer, because it does not have to deal with dynamic environment, it does not have to deal with stochastic environments, it does not have to deal with partial observability, it does not have to deal with continuous spaces. It is a much easier environment, even though it is a very hard environment by itself. And you can now come up with more examples. So, one of the significantly easier examples would be 15 puzzle. 15 puzzle is static or dynamic? Static. Deterministic or stochastic? Deterministic. Observable or partially observable? Observable. Discrete or continuous? Discrete. Sequential or episodic? Sequential. Multi-agent or single agent? Single. So, the only complexity it has is about sequentiality. And you can keep going further and further. Medical diagnosis, for example, is a dynamic environment because your body is constantly reacting to things that are happening, even though you have not taken a new medicine. It is a stochastic environment, you do not know exactly what the effect of a certain medicine would be, you do not know everything about the world, but it is a single agent problem, and so on and so forth. Why is medical diagnosis single agent? Depending upon what am I modeling in the world. What I am modeling is what should I suggest next to the patient, and so in that sense I am the only agent that is, and the human is the environment that is working, right. Now, the next thing that we have to do is think a little bit about how do we make such an agent, and what are the principles and the architectures of making such an agent. And in each such architecture, the one thing that is going to be common is that there will be the brain, which is the big red box here. So, this is the brain, the big red square, and then there will be the environment, and sensors are going to give us information about the environment, and effectors or actuators are going to change the environment, and the agent is going to output, take in these sensors and output the actions. But how we model this brain tells us what algorithm we can use. For example, let us say I model only this much in the world. I have the sensors which tell us what is the world today at this moment in time. Let us say I make some rules, if this then that, and let us say I go in the order of the rules. First one fires, output the action, if it does not fire, go to the next rule, if it fires, output the action, if it does not fire, go to the next rule. Let us call it a decision list. It is a list of decisions based on some conditions. This is what we will call a simple reflex agent, an agent which is just reflexive, which taking just reflex actions. Think about how when we take a reflex action, does it fit in this paradigm? What is a simple reflex action we can think about? I touch a hot plate, and without thinking much, I quickly remove my hand as a reflex action. Does it fit into this paradigm? We are not concerned about whether it is the am I making khichdi or am I making roti? I do not care for whether it is on a gas stove or it is on a hot plate, there are many things I do not care for. I only care for this one condition if it is hot, and I take the action, remove the hand. That will be a simple reflexive agent, and this reflexive agent also has a role to play in real robots. Can you think of one example? I think we have discussed this some time back, or maybe not. Can you think of an example where you have to put in a small reflexive agent for some specific behavior? Obstacle avoidance. My robot or drone is moving around, and the drone suddenly sees something it is going to collide with, and the drone says, oh, back up. This behavior is a reflexive behavior, it is not a deliberative behavior. Deliberative means it is thinking carefully about the outcomes and everything and then making a call. It is a reflexive behavior, and it also has a role to play in the design of a physical agent. Now, of course, we can make this reflexive agent slightly more interesting. We can say that it can keep some history about what was the world in the previous step and the new information, and based on that it can make some inference about what is the world right now, and that will be a reflex agent with some internal state about the behavior of the history so far. And notice that this part which says what was the world like, what is the new information and what is the world now is an inference step. This inference step can be done in a logical framework if the world moves deterministically, or it can be done using a Bayesian network if the world moves probabilistically. Like I get a new sensor reading and I had some uncertainty about whether the obstacle is 2 meters away or 3 meters away, and let us say my new sensor reading is 2.1 meters. Based on that I change my probability distribution of how far the obstacle is. That kind of reasoning is an inference step which I would do for sensor readings based on what the previous understanding of the world was, how the world evolves. In this case it does not evolve, the obstacle remains at its location, and what the world is now. It is still a reflexive agent because the choice of taking an action is still being done by the condition action rules. By the way, this condition action rules are extremely important in the world. I have been told in many government agencies this is what they implement. Like if they want to flag you that you have not paid your income tax, they do not want to flag all the people who have not paid the income tax, or they want to flag you for you have paid your income tax too low. So, then they will have some rules, like if your income is greater than this much amount, and if your income tax is less than this amount, and if your income is in this kind of activity, like you are a shop owner but not salaried, etc., then they will flag you and say you have paid income tax too little, give us all your papers. This is just a set of rules that the system is using to take decisions. This is something that you would apply again and again in realistic settings. But of course, we want to go beyond this. We want to have a high level understanding of what is our objective and have the system come up with the best action based on the high level understanding. And such agents can be either goal based or utility based. And think about which agent have we been working on. So, for 15 puzzle, is it a goal based agent or a utility based agent? Goal based agent. For chess, is it a goal based agent or a utility based agent? We used a utility based agent because we had to do cutoff and we had to come up with the utility of the leaf node or the cutoff node. So, we will have a goal that we want to achieve in a goal based agent. We will also have this understanding of what the world was like, how the world evolves, but additionally we will have the understanding of what my actions do. If I take a certain action in a certain state, what will be the world? And you can extrapolate it to say, if I do a sequence of actions, how will the world evolve, whether I will reach the goal or not, and then based on that I will figure out which action do I do now. All the original search based methods that we did, A star and DFS, BFS, etc., they all fit in as a goal based agent. There is a goal, there is a deliberative process which tries to figure out which sequence of actions can take me to the goal, and based on that I figure out which action do I do now. We can also have a utility based agent, and in fact in the coming weeks we will only be talking about utility based agents, because that is sometimes felt like a generalization. You know, in the real world you and I do not have a goal per se. Our goal is not like we want to make 1 crore rupees, just making this up. Our goal is the more money we make, the better it is. That is not a goal, that is sort of like a utility, that the money we make, we get some utility from the money, and then how much happiness we get some, how much health we get, everything is a number, it is not a discrete binary yes or no, it is sort of more and less, and all of those can be thought of as utilities. In fact, there is a lot of psychology theory which says that humans have some rewards built in, and we will talk more about that when we talk about Markov decision processes and reinforcement learning, which is going to come up next. So, this would be a utility based agent, everything the same, but we do not have a goal to reach, we have a utility to optimize. Everything else is the same process, except instead of saying whether I will reach the goal or not after, if I take a sequence of actions, I will ask, if I take a sequence of actions, would I be happy or not? In fact, I can't say would I be happy or not, I would say how much happy would I be based on the utility that I have, and that is my utility based agent. Notice that in everything I sort of know how the world evolves, I sort of know what my actions do. This is true for chess, this is true for 15 puzzle. But you may have an environment where you do not know everything. You have to learn about the world. Think of yourself as a baby, you do not know the environment. Think of yourself about you have just been put in a new city. You have gone tourism and you have been put in a new city. You do not know all the roads, you do not know everything. You have to learn. You have to try restaurants to figure out where to eat food, etc., etc. There you will be a learning agent, an agent which not only thinks about how the world evolves, which is given to it, but also learns how the world evolves, does some action, observes the change, learns about how the world evolves, learns about what its actions do. You know, little babies do not even know that this is their hand that they control. They slowly learn that this is their hand, and they can scratch themselves and learn their utility function, which is very interesting. Give data so that you can learn what you should be doing in the first place. Your utility function has been formed over time, it is still developing. As you come in interaction with different people, it evolves. As a little kid, your utility function is only I should get food, I should get sleep, my bottom should be clean. That is the only utility function that you have at the time. As you grow older, that is your utility function still has these 3 components, but has more. So, we learn all these phenomena, and that is what makes a learning agent. And we have done 2 small examples of learning, one in the case of learning utility function for chess or games, and one in the case of learning Bayesian networks probabilities based on data, but you will do more. We will do reinforcement learning now in a few weeks, and that is when we will really learn what is the transition function of the world, what is my reward function. All of those would be learned from the environment. So, in terms of where we are in the course, I should end this class. In terms of where we are in the course, we have done a lot of this goal based agent in a deterministic environment. We have done a little bit about utility based agent in an adversarial deterministic environment. We have also talked about how the world evolves and what my actions do, and that kind of reasoning in both deterministic environments as well as probabilistic environments. Now, we will work on building this agent, utility based agent, which knows how the world evolves, which knows what its actions do, has a utility function, it is a stochastic environment. And later we will extend it to a utility based learning agent where all these things would be learned. This part will be done through Markov decision processes, which is the next thing we are going to study, and this part will be done through reinforcement learning over Markov decision processes. So, that is our path, this is the piece of the course that is missing. We have done a lot about deterministic environment and decision making there. We have talked about knowledge representation and inference in both deterministic and stochastic environments. Now, we are going to do decision making in stochastic environments. Let us stop here, and in the next class we will start talking about decision theory. Thanks.